evening to all. Am I audible? Can anyone just send a text message so that I will start the session? Audible? Okay, I will start the session as quickly as possible. Unfortunately, because of some reason, I couldn't start exactly at 8 p.m. So it was not a serious issue, but something. That's why I just deleted all those live streaming, which I already started actually at 8 p.m., but it was not visible to you people. It's okay. I will start now. Classification of distance relays. So the distance relays, they can be classified. Actually, they can be classified as into three relays. That is impedance relay, reactance relay, and Moore relay. Further, you can classify distance relays into two groups. Okay. Further distance relays can be classified into into two groups. So those two are definite distance relay or time distance relay. So this definite distance relay, you can even call it as definite distance type impedance relay. Time distance relay, you can call it as time distance impedance relay. Okay, so both are impedance relays. But we can say these are the two types of impedance relays. Further impedance relays can be classified further into definite distance type and time distance type impedance relays. So let us see the operation of these two types of distance relays. So there is a schematic diagram of definite distance type impedance relay. So this relay, if you carefully observe, it is consisting of a pivoted beam here. This is the beam. Okay, this is the beam which is pivoted here. Okay, so it is free to move at both ends, this end and at this end it is free to move. So it is pivoted at the center. Okay, so the beam is pivoted at the center here. I will take the laser now. So it is pivoted at the center. This is the beam which is pivoted at the center. Let us some notation has been given in this diagram for the pivoted section, that is F. Okay, and if you observe carefully, there are two electromagnets. Okay, this one electromagnet and this is one electromagnet. There are two electromagnets which are energized by their respective current and voltage transformers, that is CT and PT. So you can see here on the left side, from PT, voltage is given to this electromagnet, and on the right side from this CT, current is given to this electromagnet. So the input to this electromagnet is voltage from the PT, and input to this electromagnet is current from this CT. Okay, so this portion, rectangular portion which is shown here, okay, they are called as armatures. These two are the armatures. Okay, so the armatures of these two electromagnets, they are mechanically coupled to the beam, that is this beam, okay, they are mechanically coupled to the beam on the opposite sides of the fulcrum. So here you can see here, we just on the above this beam there is a moving contact, black portion. What you can see here, there is the moving contact. These two dots, they are the fixed contacts, okay, of your trip circuit. So this relay, it has been designed in such a way that initially under normal operating condition, torque produced by the two electromagnets, they will be in opposite direction to each other. Means both the torques will oppose each other. So here, if you here actually the torque produced because of this voltage that has been given to this electromagnet is the restraining torque. Okay, and the torque that is induced here because of the current that is flowing through this coil is the operating torque. So under normal operating condition, restraining torque will be greater than the operating torque. Therefore, this beam will be somewhat tilted towards this electromagnet, left side electromagnet. Okay. So when this beam is tilted towards this left side electromagnet, definitely this moving contact will be away from the fixed contacts. So now if fault occurs, the fault current will increase, the CT will sense the fault current, and when the fault current increases in the relay coil, this coil you can call it as relay coil. So when current increases in the relay coil, what will happen is the torque produced here, the operating torque produced in this electromagnet will become greater than the torque produced in this electromagnet, restraining torque produced in this electromagnet. Therefore, this armature is attracted towards this electromagnet. In other words, instead of using the term torque, what I can say is we already know when a ferromagnetic material is wounded by a coil and when current flows to this coil, this electromagnet gets magnetic property and this armature will be attracted towards the magnet. That is under normal operating condition. When the current flowing through this coil, when fault occurs, current flowing through this coil increases, automatically what will happen? The flux density of this flux density in this electromagnet will become greater than the flux density in this electromagnet. So this armature will be attracted uh, towards this electromagnet. Hence, when this armature is attracted towards this electromagnet, automatically this moving contact will come in contact with these two fixed contacts, and trip circuit is closed, and hence trip coil is energized, and hence what will happen? Circuit breaker is open. I will just take a pen. So, okay, that's what happens. So the torque, sorry. So the torque that is developed in this electromagnet is restraining torque. The torque that is developed in this electromagnet is operating torque. So here this restraining torque will be proportional to the, as I said, my cursor is sensitive, even though it is sensitive, I won't stop using it. That's the issue. So the restraining torque will be always here voltage is the input. So restraining torque that is developed in this electromagnet will be proportional to the square of the voltage, and the operating torque that is developed in this armature will be proportional to the square of the current. I wanted to write I and I couldn't write I. Restraining torque is proportional to the square of the voltage, and operating torque is proportional to the square of the current. If you remove the proportionality, you can replace it with some proportionality constants. What I can say is it's better if I take text and it's better if I take some this text and I write. So this tau r, you can replace proportionality with some proportionality constant, some k1 into v square. Okay, square is not there. Okay, it's okay. It's not possible. So there is no option to consider this as square. This as square. So yeah, now I can do this. So v square. Just increase this. I don't know whether it is visible to people or not. And this r should be in the subscript. 1 should also be the subscript. So tau r is equal to k1 v square. Similarly, tau naught. So simply by removing the proportionality, you can replace with proportionality constants, some k1 and k2. So under normal operating condition, tau r will be greater than tau naught. Okay, and when relay starts to operate, tau r will become less than tau naught. Means tau naught is greater than tau r. So, and when relay is operating, what is happening here in the next slide? If you see here, k1 v square is less than k2 I square. So why k1 v square is less than k2 I square? K1 v square means what? K1 v square means tau r, k2 I square means tau naught. So when relay operates, k2 I square will become greater than the k1 v square. Okay, so you can simply rearrange the terms. Simply what I have done here is I square I have sent it to the left side, k1 I have sent it to the right side. So v square by I square is less than k2 by k1. So I have sent this square to the right side. So v by I is less than or equal to root of k2 by k1. V by I is nothing but z. Z is less than root of k2 by k1. Okay, so what is Z? Z is the impedance. So Z is the impedance here, which is less than k2 by k1. So the values of these constants k1 and k2, it will always depends on the ampere turns ratio of the electromagnets. Okay, so we can even provide proper tapping to change the k1 and k2 values. So that's it. Its operation is simple. Simply whenever fault occurs, the current flowing through this coil will increase for this electromagnet, and operating torque will become greater than the restraining torque. Hence this armature is attracted towards this electromagnet, and hence the moving contact comes in contact with this fixed contacts, and the relay operates. Or we can say trip circuit is closed and circuit breaker is open. So this is how definite distance relay operates. Okay, let's go to the next one, that is time distance relay. This is time distance relay. So in this time distance relay, so it is, we can even call this as well time distance impedance relay. So this relay, it has a property. The property is that it can automatically adjust its operating time according to the distance of the relay from the fault point. Okay, so according to the distance between the location of the fault and the location of the relay, based on that, this relay can automatically adjust the distance. Okay, so the operating torque will be directly proportional to the distance. So operating not torque, operating time of the relay. Okay, time of operation of the relay will be directly proportional to the distance. So as distance varies, the operating time will also vary. So distance means here we are going to measure the ratio of voltage and current. Therefore here time of, this is not torque, this is time of operation. The time of operation of the relay. Okay, so here I have written T, but here at this moment this is not torque. The time of operation of the relay will be directly proportional to the distance at which the fault has occurred. As the distance as the distance of, means as the fault occurring distance varies, automatically the time of operation will also vary. So the time of operation of this relay is not fixed. Okay, whereas in the previous case, which I didn't mention, but the time of operation of this relay is always fixed irrespective of at what location the fault has occurred. But for this particular relay, the time of operation will vary depending on the location of the fault. Okay, so if you observe here, let us start with the bottom. In the bottom, there is an induction type overcurrent relay. So you just observe here, there are two electromagnets, upper E-shaped electromagnet. This is E-shaped. My cursor, it will be always irritating me. It's okay. This is E-shaped electromagnet. This is our U-shaped electromagnet, and in between E-shape and U-shape there is a disc. In between E-shape, I will take this laser instead of pen. Yeah, this is our E-shaped electromagnet. This is our U-shaped electromagnet. In between E-shape and U-shape electromagnet, there is a disc which is free to rotate. Okay. So, and if you observe here, this disc which is free to rotate here, it is connected to a spindle. That spindle is it is passing through the central limb of the upper electromagnet, and it is see here, it is attached to some structure here, some frame we can say. To that, a spiral spring coupling is connected. Okay. Yes, it is made up of metal, but it is it means it can rotate, it can twist. Okay, the spiral spring can twist if required. And one more straight what to say, straight rod, we can say a rod is connected here. Okay, and to that an armature is fixed. This armature is attached to an electromagnet here, and this straight rod, whatever is there, that is connected, moving contact is connected to that rod. So now here we can see potential transformer means voltage is given here to this coil from the potential transformer. From the CT, current is given to this electromagnet. So initially we already know that restraining torque will be greater than the operating torque. So initially this armature is attracted towards this U-shaped electromagnet, upper U-shaped electromagnet. There are two U-shaped electromagnets here. This is the upper one, this is the lower one. So this armature is attracted towards this U-shaped electromagnet. Because this armature is attracted towards this U-shaped electromagnet, the rod, it is not moving, it is in a fixed position. Because of that fixed position of this rod, what will happen is this moving contact will be away from the fixed contacts of your fifth circuit. Okay. So use this upper electromagnet, U-shaped upper electromagnet, you can call it as voltage restraining magnet. Are you able to follow? Is there any disturbance? Can anyone just mention in the chat box? It seems no one is there in the class. No one is there in the class, then I will quit the class. What is the name? Is there anyone? Okay. No disturbance? Okay then. But here it is showing no concurrent viewers, and you are responding. But here it is showing no concurrent viewers. I thought no one is there in this session, and I will just quit the. I just wanted to quit this session because it is not showing the number of people watching. It is not showing anyone at all. Okay, concurrent viewers are on 0. It is showing. Okay, I will see 5 more minutes. After that, you will see. Okay, this is it. Here, lower electromagnet is there. I will take the laser. Okay. So in this is the upper U-shaped electromagnet, and this you can call it as voltage restraining magnet, and this lower U-shaped electromagnet is there. Okay. So I am talking again and again about this lower. I thought you may get confused if you are listening to the class. You may get confused between these two U-shaped electromagnets. But the main purpose of this upper U-shaped electromagnet is to produce the required restraining torque. So when normal current is there in the given circuit, the potential transformer will measure the voltage, and the voltage is given as input to this coil, and hence this coil will make sure this armature is attracted towards this electromagnet. So under normal operating condition, the upper armature, this armature is attracted toward this upper electromagnet. Now when fault occurs, the fault current, the CT will sense the fault current, and because of that what will happen is here in the central limb flux is induced. So when flux is induced in the central limb, that flux will cut the this winding, that is secondary winding, isn't it? This coil acts as the primary winding, and this coil, it acts as the secondary winding. So when this flux lines cut the secondary winding, what will happen? EMF is induced, and since this coil is forming a closed path, what will happen is current will start to flow through this secondary coil, and when current flows to the secondary coil, what will happen is this U-shaped electromagnet gets magnetized. Now two fluxes are induced here. In the upper electromagnet, some phi1 flux is induced. In the lower electromagnet, some phi2 flux is induced. So I think I am going to conclude this session after this topic, because there are no concurrent viewers for today's session. Okay, your wish. What can I do if you are not interested? What can I do for that? Okay. So here phi1 is the flux induced in the upper electron, phi2 is here in the lower electromagnet. Due to interaction of these two fluxes, two torques will be induced in this disk, and the resultant torque will cause this disk to rotate. Okay, so resultant torque, net torque, will cause this disk to rotate. When this disk rotates, automatically this rod is there. Okay, when this starts to rotate, this rod will also starts to rotate. When this rod rotates, you can see some frame that is here, and a spiral coupling spring is connected above it. So what will happen? So this spring gets twisted. When the spring gets twisted, automatically this rod starts to move. Okay, so after this armature, which is being already attracted by this this upper electromagnet, that armature is pulled away from this upper electromagnet. Okay, because this spindle, we can say, okay, this spindle or rod starts to rotate because of the rotation of this spiral spring coupling element that is provided here. Why this spiral spring coupling element is twisted? It just twists, it won't rotate, it just gets twisted. Why it is getting twisted? Because this rod started to rotate. Why this rod started to rotate? This rod, why it started to rotate? Because this disc started to rotate. Why this disc started to rotate? Why? Because of the fluxes that are induced in the upper electromagnet and lower electromagnet. Because of the interaction of these fluxes with the circulating currents that are induced in this disc, net torque will cause this disc to rotate. So when the net torque causes this disc to rotate, automatically the spiral spring rotates and the upper rod rotates. Armature is pulled away from this upper electromagnet. So hence what will happen? Moving contact will come in contact with the fixed contact, and trip circuit is closed, and trip coil is energized, and circuit breaker is open. Okay, so this is the operation of this relay. Okay, I think since only 2-3 members are watching, I will conclude this. I wanted to discuss some other topic, that is static relays. I wanted to discuss static relays, but since only 3 people are there, I will conclude this session. Okay, how many of you are watching? Can you just mention? I could see only here. You can see, if you see carefully the screen, it is mentioned only 3 concurrent viewers are there. 3, not 3, sorry, 0. It is showing only 0. So it's better I will end this session. If no one is joining, what is the need to conduct this session? It's wastage of my time. Okay. So yeah, you can see now it is, see, it is visible, isn't it? Zero concurrent viewers it is showing. Okay, so we are in this session. Only two people are in this session. You can see in your own mobile. You can see how many people are watching, isn't it? Yes or no? See how many people are watching. Now it is showing only 3 members. Okay, so among those three, I am the one. Okay, among those three watching members, I am the one who is watching. Okay, whoever is watching, yeah, 3 members. Among three, I am the one who is watching. So, do you want me to continue? Yeah, only 3 members, sir. Among three, I am the one. Means only two people are watching. No one else. Yeah. Yesterday's session, approximately there were 10 people who have watched, and today it has reduced. Okay, and compared to yesterday's session. So it's okay then. I will just conclude what's the need, huh? It's wastage of time for me. Okay, I'm concluding this session as only 2 members have joined except me, and now it has increased to 3. It's okay, it's okay. Your wish. If you are not interested, I should not force you, isn't it? It's your wish. You might be having many important things than joining this session. Okay, okay then. You can leave. You people can leave, or okay, you can leave the session. You can leave. అయిపోయింది ఇంకా లైవ్ లో ఉంది కదా. Okay, I'm ending this session as very few members are there in this session. Okay then.